We've already been using functions which support extended argument syntax, although you may not have realized it. For example, have you wondered how it's possible for print to accept 0, 1, 2, or in fact any number of arguments? Another example we've seen is the use of the str format method, which can accept arbitrary named arguments corresponding to the format placeholders in the string. In this section, we'll learn how to define functions, or more generally callables, which can accept arbitrary positional or keyword arguments. Let's start with positional arguments. Drawing an example from geometry, let's write a function which can return the area of a two-dimensional rectangle, the volume of a three-dimensional cuboid, or indeed the hypervolume of an n-dimensional hypercuboid. Such a function needs to accept an arbitrary number of numeric arguments and multiply them together. To do this, we use a special argument syntax where the argument name is prefixed with a single asterisk. Before we implement the computation, we'll simply print out the value of args and its type using the built-in type function. Notice that the asterisk does not form part of the argument name, and the argument name we have chosen here, args, is widely used in this case by convention, although is by no means necessary. Colloquially, this form is called *args. Now let's call our function a few times. We can see that args is passed as a tuple which contains the function arguments. Knowing this, it's a simple matter to write code to multiply all the values in the tuple together to get the result. Redefining hypervolume and using a more documentary name for the argument gives us this. The function works by obtaining an iterator I over the tuple and using the next built-in to retrieve the first value, which is used to initialize a variable v in which the final volume will be accumulated. We then use a for loop to continue iteration with the same iterator to deal with the remainder of the values. We can use the function to compute the areas of rectangles, the volumes of cuboids, and the hypervolumes of hypercuboids. It also generalizes nicely down to lower dimensions to give us the length of lines. However, if called with no arguments, the function raises stop iteration, exposing an implementation detail about which clients of our function should be unaware. There are a couple of approaches to fixing this. One change could be to wrap the call to next in a try except construct and translate the exception into something more meaningful for the caller, such as the type error that is usually raised when an insufficient number of arguments is passed to a function. We'll take a different approach of using a regular positional argument for the first length and the *args to soak up any further length arguments. Using this design, the function continues to work as expected when arguments are supplied, and raises a predictable type error exception when insufficient arguments are given. At the same time, the revised implementation is even simpler and easier to understand than the previous version which used an iterator. When you need to accept a variable number of arguments with a positive lower bound, you should consider this practice of using regular position arguments for the required parameters and *args to deal with any extra arguments. The *arg syntax only collects positional arguments, and a complementary syntax is provided for handling keyword arguments. Let's look at that now. Arbitrary keyword arguments can be accepted by callables that use an argument prefixed by a double asterisk. Conventionally, this argument is called kwargs, although depending on your situation you may care to choose a more meaningful name. Let's make a function which returns a single HTML tag as a string. The first argument to the function will be a regular positional argument which will accept the tag name. This will be followed by the arbitrary keyword-args construct, to which tag attributes can be passed. As before, we'll perform a simple experiment to determine how the keyword arguments are delivered, by printing the keyword-args and the type of the keyword-args. When we call the function with some suitable attributes to create an HTML image tag, like this, we can see that the arguments are transferred to our keyword arguments formal parameter as a regular Python dictionary, where each key is a string bearing the actual argument name. Note that as with any other Python dictionary, the ordering of the arguments is not preserved. Now we'll go ahead and implement our tag function properly using a more descriptive name than kwargs. Here we iterate over the names in the attributes dictionary, building up the result string as we go. It's worth pointing out at this stage that this struct format method we call here also uses the arbitrary keyword args technique to allow us to pass arbitrary named arguments corresponding to our replacement fields in the format string. This example also shows that it's quite possible to combine positional arguments and keyword arguments. In fact, the overall syntax is very powerful so long as we respect the order of the arguments we define. First, star args, if present, must always precede double star keyword args, so this isn't allowed. Second, any arguments preceding star args are taken to be regular positional arguments, as we saw in the hypervolume example earlier. Thirdly, any regular arguments after star args must be passed as mandatory keyword arguments. Failure to do so results in a type error. Fourthly and finally, we have the double star keyword args arbitrary keyword arguments, which if present must be last in the argument list. Any attempt to define an additional formal argument after double star keyword args results in a syntax error. You should take particular care when combining these language features with default arguments, which have their own ordering rules specifying that mandatory arguments must be specified before optional arguments at the call site. Before moving on, we should point out that all of the features of the extended formal argument syntax apply equally to regular functions, lambdas, and other callables,